This is my laptop running at full capacity using the GPU to do physics. In a previous video, I made this physics simulator, but it has one small problem. It gets very slow once I add like 300 objects, and that's because each and every object in the scene needs to check if it collides with all other 300 objects, leading to an n-squared algorithm and 90,000 checks. And you might say, great, you have to improve the complexity to solve the problem. But that involves algorithms and data structures, and I hate that. So instead, I'm going to implement a physics engine on the GPU. And it literally moves slower than the one on the CPU. So a CPU has a few cores, like 8 maybe, and each core can do quite a ton of cool stuff. A GPU, however, has thousands of cores. The only catch is that they are very dumb, and they all need to execute the same thing at the exact same time. Think of a GPU as a classroom of toddlers with crayons, but like 1000 toddlers. Sure, they can color really fast, but good luck getting them to draw anything that makes sense without eating their crayons first. In fact, you can't even use a single thread at a time. One GPU core has actually 32 units that all execute the same instruction, so you always execute a multiple of 32 threads. And if you need only one thread to execute, there will be other 31 threads executing, but marked as inactive, so they don't actually write any data even though they execute. And you can harness the power of the GPU using what are called compute shaders. Those are basically some small C-like programs, and we run a ton of them in parallel. But let's implement the simulation on the CPU first. And if you are new to my channel, you probably know that I'm into GPU programming and OpenGL and stuff, but I was always afraid of compute shaders for some reason. So soon I will be writing my first compute shader. So I decided to make the simulation in 3D, because why make my life easier? And here we have a cube. And as I explained in the last physics video, if we drop an object, it should return to the same height, and that is what we have so far. But now we need to implement collisions. So collisions work something like this. If two objects move towards one another and we detect that they intersect, we need to find the collision normal and push them both using that direction. And this is easy for spheres. We just use the vector from one sphere to another as the collision normal. And now we've got balls collision. Now I just need to implement cube versus cube, sphere versus sphere, cylinder versus cylinder, cylinder versus sphere, cylinder versus cube. This took forever, but here it is. And you can get to like a few hundred objects at 60 FPS, or 3000 objects for like 4 FPS. But now, let's start moving it to the GPU. So this is how it will work. Normally, we collide each object with every other one, so we get 2 for loops. Using the GPU, however, we can create a thread for each object in the scene. So essentially, it's like we completely get rid of the first for loop, getting us to an O of n algorithm. Writing the compute shader itself wasn't hard at all actually. I just had to copy the code from the CPU to the shader and solve some compiler errors. Architecturing the setup itself was more difficult, and I'll talk about that in just a second. But with that, it was finally time to write my first compute dispatch in my life. So I was hyped for this moment. So this is the first attempt, and it literally moves slower than the one on the CPU. And get this, the dedicated GPU performs worse than using the integrated one. So what's going on? This is how the simulation is currently working. In order to communicate with the GPU, we use what are called buffers. They are just blocks of memory on the GPU, and we have 2 buffers where we store the geometry. From one we read and we write into the other one. We send them to the GPU and it will compute all the things. Then we read the result back and use them to display the shapes. In the next frame, we swap them and repeat the process. But can you see the problem? We send data 3 times. One time to send the geometry, one to read the geometry back, and finally we send it again to the GPU to be drawn. The GPU is indeed very fast, but it has its own memory, so it takes time to send data to him. Looking at this diagram again, I think you can see that we can ideally just always keep the data on the GPU and never send it back to the CPU. We compute the physics simulation, and then we send the data to the drawing shader. We swap the buffers, and we repeat. So I started to investigate a little, and I found that there was another function to read the data from the GPU that was way faster, and after I switched to that, it started getting some good results. 25 FPS for 7000 objects. That's not bad, but we can do better. So whenever you want to optimize something, the most important thing to do is to measure. So I did some graphs, and you can clearly see that reading the data can take like half of the frame time. So I also did some small tweaks, like looking at n-sight again. Apparently, it matters how you choose your size of your compute subgroups to use the GPU efficiently. And I expected the driver to do this for me, but that's why you need to measure. Okay, so now we need somehow to take this data and render it. And what I will do is I will move it at the end of the shader into 3 different buffers, one for each shape. And remember that each shape will be executed in a different thread. So I'm using some atomic counters to get a different position for each shape. Then I use instance rendering and read the size and the position for each shape from this buffer, and that's it. Weirdly, the speed up wasn't as much as expected, only a few milliseconds, and that's because the GPU is very smart nowadays. So even though we weren't doing the optimal thing earlier, the GPU was doing some other work to not waste time. So now if I put my laptop into rocket mode, where it basically feels like I'm having a private jet engine, I get 60 FPS for 4000 objects, and the max I managed to get it is to 10,000 objects at 10 FPS. So I think that's good enough. And I know I skipped a lot of details regarding the physics simulation itself. So if you are interested about how to actually make a physics simulation, I have it all in this video. See you there. Or don't, I don't know, I'm not your boss, but just saying, I might know where you live, so think about that.